Hi and welcome to Unit 2, Topic 3, Video 23. And in this last couple of videos, we're going to clean up a couple of loose ends, and then we'll be finished for this topic. So in this video, it's inverse transformations. Now, inverse transformations sounds exactly like it is, and it's just a build-up of some of the skills you've learned in this topic, applied all at once. There's our learning goals, success criteria if you'd like to have a read of them. Well, what do we know? Well, if A is a transformational matrix, usually written as A, B, C, D, and X is a coordinate or maybe a shape, which is usually represented by a 2 by n matrix, where n represents the number of vertices the shape has, well, then we know that AX is equal to X dash. So the transformation matrix times by the coordinate or the shape is equal to, and this is the original, is equal to the image of the coordinate or the shape. So we're pretty happy with that. What it means though in purple is that if we took A inverse of both sides, that's the inverse of the transformational matrix, then X will equal A inverse X dash. So if we know the image, which let's be honest, often we might know the end result and want to know where did this come from, we can determine the original. And we also need to recall there in orange that A inverse equals 1 over the determinant of A times by D negative B negative C A. So the Cambridge textbook lists quite a few common ones that'll come out of this. Now, there's no reason at all to go through memorising these. Note here that this requires some knowledge of odd and even functions. Again, that comes through in our topic 2, unit 2, so you'll see it soon if you haven't already. But you don't really need to memorise these. What's important here is just note, look, K and 1 over K. That's probably what you'd expect for an inverse. K and 1 over K. K and negative K is another type of inverse we might get. These reflections are kind of as you'd expect as well. If you reflect over the x-axis once, and then you want to go back, well, you just reflect over the x-axis again. Does that make sense? So we get the same matrix that's self-invertible. So there's our information. Now, there's some notes here as well, but again, you can have a read of those proofs if you need to. So we're going to talk about inverses, and I've got a couple of examples for you. Example 1 we'll start with. A transformational matrix takes xy to 2x minus y, 4x plus 3y. So we're asked, well, A times x equals x dash, and we know that A times xy is equal to 2x minus y, 4x plus 3y. Now you can go through some stuff with A, B, C, D, etc., but it's not too hard to work out that A is equal to 2 minus 1, 4, 3. It's the coefficients of x and y there. So a little bit like that simultaneous equation stuff we did earlier in this topic as well. So there's our transformational matrix. But in this case, we know the image. So we've got A times a point P is equal to P dash. That means that let's leave it like this. It means that P, A inverse A, P equals A inverse P dash. And that means that P, the original point, is A inverse P dash. So we need to know A inverse. And A inverse in this case is 1 over the determinant of A times by 3, 1, negative 4, 2, and the determinant of A, det A, is equal to 2 times 3 minus negative 1 times 4. And that's equal to 10. Okay, so we've got some information there that's going to really help us. We can now say that A inverse is equal to 0.3, well actually I might do its fractions, 3 over 10, 1 over 10, negative 4 over 10, and 2 over 10. I could simplify some of those, but I'm going to leave it. 10 is a really nice denominator, so let's leave it as 10. And that means that P is equal to 3 over 10, 1 over 10, negative 4 over 10, 2 over 10, times by our image point, 7, negative 1. This is P dash. 3 tenths of 7 is 21 tenths minus 1 tenth is 20 tenths. And negative 28 tenths minus 2 tenths is negative 30 tenths. And of course we can simplify that down to 2, negative 3. So the original point was 2, negative 3, and that got us to the image point 7, negative 1. We could check this now by just doing A times the original point, and that should give us 7, negative 1. Okay, let's have a look at a second example. A triangle is rotated clockwise about the origin, 90 degrees, then flipped over the y-axis to arrive at the image coordinates there. So we've got the same situation. We've got the image coordinates. So we've got A, P equals P dash, and we're told that let's forget A for a second. P dash is equal to -1, -1, -2, -2, -2, -3. And we also know that A is equal to, the second thing is flipped over the y-axis. Remember that flipping over the y-axis means we're making that negative x, so -1, 0, 0, 1. And 90 degrees clockwise is cos of -90, sine of -90, sine of -90, and cos of -90. And that one there's the negative. So you get -1, 0, 0, 1. Cos of -90 is 0. Sine of -90 is -1, so that becomes 1, -1, 0. We multiply that out and we get 0. And then we get -1, -1, 0. So that's our resultant transformational matrix. And we've got I'll just scroll this down to here. AP equals P dash, which leads to A inverse AP equals A inverse P dash, and A inverse A is the identity, so therefore P is equal to A inverse P dash. So we need our A inverse, and in this case the determinant of A is equal to 0 minus -1 times -1, which is equal to -1, and so therefore A inverse is 1 over -1 times by 0. The B and C become positive, so 1, 1, 0. That's equal to 0, -1, -1, 0. And so it's actually self-invertible. A inverse and A are the same. That's interesting. If you rotate 90 degrees and then flip it over the y-axis and then do that again, you must get back to where you started. That's what self-invertible is. And so P is going to be equal to 0, -1, -1, 0 times by the original, the image coordinates, -1, -1, -2, -2, -2, -3. And that's going to be equal to this top line. So the top row multiplied by each of these columns eradicates the top value and makes the bottom value negative. So we end up with, started with a negative there, 1, 2, 3. And this one does the same but with the top. So 1, 2, 2. And there's my original coordinates for the shape. But the actual original coordinates are 1, 1, 2, 2, and 3, 2. Always go back and make sure we've answered the questions. Triangle is rotated 90 degrees clockwise around the origin and flipped over the y-axis. Oh yeah, I see. Turns out there's no question here. But anyway, we've found the original coordinates where that was not really asked, nor was anything else. Good times. So there's a couple of examples. You can find the original coordinates of a point or a shape if you know the image coordinate by using the inverse of the transformational matrix. All the best.